Conservation of momentum. Conservation means what? The same or kept, right? Oh, I knew how I was going to start this. Okay, I won't. I was gonna talk about the Astro Blaster but yeah, we did the TED Talk instead. We'll do it this way. Okay, so after this, you're gonna understand conservation of momentum as it relates to one-dimensional collisions. Now, on the first day, I gave you sort of the problem examples or what they were going to be. One-dimensional collisions are clearly the easiest. Okay, so today we're going to be talking about collisions. Tomorrow I'll probably talk about explosions, but they're really just collisions in reverse. So the general principle is sort of the same. So those of you that are away tomorrow, if there's time, I might even be able to go through it with you. Okay, so, and I prepared some sheets for you. I did that for you last night. So you didn't have to write everything down so we could get a little bit farther along. So the law of conservation of momentum states, I think is what you have, and then you have to write, when no net external forces are acting on a system of objects, the total vector momentum of the system remains constant. I think there's a spot there for you to write this in. Okay? The total vector momentum of the system remains the same. Vector momentum. Not so much a big deal in one-dimensional, but when we get to two-dimensional, it will be. Are you dreading two-dimensional vector collisions? I've sort of hyped them up a bit, haven't I? When no net external forces are acting on a system. So there's no outside forces. The total vector momentum of the system remains constant. Now, what does that mean in English? I guess, okay, in one way. In English, the momentum before is equal to the momentum after. The momentum before is equal to the momentum after, provided that there are no, that should be no, not. Not, I guess no, there are not other forces acting. The momentum before is equal to the momentum after. You could look at it like this. The change in momentum is zero. Will there be various momentums? Yes, but the total of them will be zero. Now, how do we put this algebraically? I start every question with Pi is equal to Pf. And that's just a framework, a way of thinking. Pi stands for initial momentum, Pf, final momentum. Momentum must be conserved. Now, does this always happen in real life? No. There's always friction present that sort of takes away things. But generally, momentum is conserved. Good to go? Yeah? Okay, so here we have a diagram, and you have it there in front of you. Man and boy. Boy has a mass of 40 kilograms. Man has a mass of conveniently twice as much, 80 kilograms. And he gives him a shove in the back, and the kid goes ahead at 0.5 meters per second, and the man goes back at 0.25. Do any of those sort of numbers surprise you? Right? If the man is twice as big, he's going to go half as fast, right? That made it nice and easy, kind of thing, right? So, what is the total momentum before? This is initial. This is the final. What is the total momentum before? How come? No motion. Velocities are zero. Total momentum before is zero. What about after? Dan says still zero. But they're moving down. Opposite directions, right? You are. So PB.
Why does he know that? But like cancel each other out.
Cancel each other out, exactly. Negative, positive. PB, momentum boy, would be mass of boy times velocity boy, and I warned you about the subscripts. MB stands for, Blair? Mass boy. VB, velocity boy. So the mass of the boy is 40, and the velocity of the boy is minus 0.5, which is minus 20 kilogram meters per second. Right? And in the same vein, momentum man would be mass man times velocity man. Cheech and Chong movie. You guys are too young for that. Mass man, 80, velocity man, 0.25. What do you know? 20 kilograms per second. And as pointed out earlier, they are balanced. Minus 20 and 20. So what is the total momentum? Just like predicted, 0.
Why is the boy's momentum backwards?
Because he's moving to the left.
Okay.
Right? So his velocity is left.
Does it matter which one is it?
Well, usually left is negative, so, right? Yeah. You could define right to be negative if you want, but in the middle it's got the constant. So the total momentum at the start is 0, and the total momentum after is 0. Is momentum conserved? Absolutely. Now, that's about as simple a situation as you get, right? Is the man always going to be exactly twice as much as the boy? And
Oh, I hope so.
well, boy, oh boy, you're wrong. Now, the first time I started talking about momentum boy and mass, or velocity boy and stuff, it kind of made me think of superheroes. And there he is there, yes. You've seen him on the wall, that's where he came from. So I talked about momentum boy. So my good friend Garrett Fletcher, Dawson's brother, drew me this picture. Said, there you go, Mr. Man, that's momentum boy. I keep the universe safe by changing my mass or velocity. He has superpowers. And then we never did decide whether momentum boy grew up to be momentum man or that was just his partner in crime, or in fighting crime. Yeah. Come on, give me a little smile hand. Try to make your day a little brighter. Should try it. Okay. Inelastic collisions. I guess that's the whole thing, isn't it? Yeah. Silly. Inelastic collisions. Suppose we have two carts of equal mass traveling at the same speed, but towards one another. Now, if there's no rebound effect because they hook together, this is an example of an inelastic collision of one dimension. All you really got to write down is inelastic means no rebound. Let me demonstrate. I knew I should have practiced. Always forget. On pause there?
It's winter.
Actually, no, it's not winter.
Hate it when people play back here.
It's winter.
What?
Looks like this, but it doesn't say magnetic on it. There's one of those that both magnetic. Oh, is there another one? Oh! Silly momentum, man.
Wait.
I didn't know. I know it wasn't you guys. Okay, so let's do some math with this. Do you have that picture? No?
No, you have a different picture.
Okay. So just, yeah, so you're still on the front page. You're still on the front page. So you can just draw that picture. The momentum of part A, which is, I guess, technically PA, would be equal to MAVA, mass A times velocity A. Momentum of part B, which would be PB, which would be mass B times velocity, MBV. Okay, you guys, you have that there already, right? You just need to draw the picture. Okay, so would you agree that velocity A is equal to negative velocity B? Like if the velocity of A is, which one is A? If A is to the right, which is positive, right? So velocity A is, we'll say plus 5. If this is minus 5, well then minus 5 would be plus 5, right? So VA is equal to minus VB. They're equal but opposite. Does that mean then that MAVA is equal to MBVB? It does, because the mass of A is equal to 500 grams, and the mass of B is also 500, which means that MA is equal to MB. They're equal parts. MAVA is equal to minus MBVB. With me so far? So if MAVA is equal to minus MBVB, when you take that MBVB to the other side, it becomes positive, where you're going to get MAVA plus MBVB is equal to 0. The total momentum before has to be 0. The two carts are the same mass, traveling together at the same speed, just different directions, and so, mathematically, the total momentum before is equal to 0. And if the total momentum before has to be equal to 0, that tells us the total momentum after is also 0. And that's the key idea. The hard part about all this is all the writing it down, right? Like all the subscripts and all that mumbo jumbo stuff. That's the hard part. But the basic idea is pretty easy.
Basically, it's either stops before or after, then the momentum is 0.
Exactly. Now, does it have to be 0?
If it stops, yes.
Fair enough. But later on, we're going to get to this kind of situation where the cart's going like this, and then this one goes, right? So is the momentum before 0? No. Is the momentum after? So I just want you to get that idea. But if either one is 0, well then, or either one is stopped, right? Okay. So this is true if this is an isolated system. Both parts had kinetic energy before the collision. Do you agree? Now, we haven't talked about kinetic energy. Don't even bother writing that down. This is just an aside. Don't even bother writing this. Would you agree that both carts had kinetic energy before? Absolutely. How much kinetic energy is there at the end? 0. It's not moving. Is energy not conserved as well? The answer is yes. So where does this kinetic energy go? Where does this energy go? Energy isn't a vector. Oh. Well, if you could have a really, really accurate thermometer, you would find that there's some heat created. Okay. Where does that energy go? It becomes heat. Hannah, are you looking at math in here? Now, I used to have, I'll have to look for them. I haven't found them for a while. I used to have 2 really heavy, shiny metal spheres. And when you slam them together, there's a lot of kinetic energy transferred to heat energy, and if you put a piece of paper in between them, actually yes.
Really? Ooh, what happened?
What did Laura do? Not quite. You're really close. I'll see if I can find it. You get fire, yes. You do. You get fire. Oh, I know. Again, people got to stop playing around in my toy chest back there. People, the kids, they want to stand at it, that's what they do. And you guys are guilty of this. You don't play, but you all go stand by the door, right? And if there's more than 30 seconds, ooh, look at this, ooh, and next thing you know, something's busted or walking out the door. Which is why I yell at you for standing by the door. I'll see if I can find it. Because that's way more fun than what we're about to do. If one card has a greater mass and the velocities remain the same, what will the outcome be? So I'm going to go get out of the 500 gram weight. Okay, so now the card on the left, no, I wanted the card on the right, E. Okay, so the card on my left, your right, is now twice as massive. Okay, what happens when I push them together at the same speed? Will it's going to go this way? Why is it slow down eventually? There is a little bit of friction, right? Now, were those exactly the same speed? The speed wasn't quite the same though, was it? Eh? What if this one goes faster? How fast would it have to go to make it stop in the middle?
Twice as fast?
Twice as fast. See if I can do it.
Ah!
Almost like I'd practiced it. Let's do the boring math that goes with it. Great question, Red. Suppose the mass of A is 100 grams, the mass of B is 200 grams. Doesn't matter what they are, we're just going with 100 and 200 because they're easy numbers to work with, right? And I'll say that the velocity of A is 2 and the velocity of B is minus 2. Do you guys have this?
Yeah.
Awesome. I was smart. Okay, so the question really is, what will happen? What will be the momentum, or what will happen at the end? Okay, so what is the total momentum before? Okay, the total momentum before is made up of the momentum of card A and the momentum of card B. If you want, you want to put this step, PI is, I guess it would be PA plus PEB. I think we can skip to the next step. It's up to you. So the total momentum before PI is MAVA plus MBVB. I've done this a lot. I know.
I think it's M delta.
Oh, the A? Yeah, kind of looks like MAVA plus MBVB. Okay, so let's figure out what this momentum is. So, should it be in kilograms? Yeah, it probably should. Those should probably be decimals. So, the initial momentum, PI, is 0.1, that's our mass of A, times 2 meters per second, plus 0.2 times minus 2. Now, I've thrown easy numbers in there that you could hopefully multiply in your head. 0.1 times 2 and 0.2 times minus 2 should give you, yeah, that's going to be negative, that's going to be 0.2 and that's going to be negative 0.4, which should give you a negative 0.2 kilogram meters per second, right? So the total momentum before is not 0, which automatically tells you when they collide, what will the velocity be? Not 0.
Right.
It will not be stopped, right? It will not be stopped because it wasn't 0. Does that make sense, Sarah? Yeah? Good? Okay, so now let's find out what's happening after. The total momentum before and after, PI and PF are the same, is that 0.2. Oh. Yeah, why is that positive? I've never spotted that before. Darn mistakes. It should be negative, and that's crucial too. Gotta fix this. Apologize. I'm glad you spotted. Now, we haven't talked about this yet. What's the mass of the combined carts at the end? Does that matter? Yes, it matters. What happens to the masses? Like before, when it was simple, and I probably should have talked about this. What? I got these are. I know these are 500. So 500 and 500, when they come together, what's the mass? 1,000, right?
You clean it from here?
I think I'm out. Sorry. Yes, sorry. Am I good here? Can I go on? Hannah? Okay, that's fine. The question will be, find the velocity of the combined system. How fast are the two carts going when we're all done? Let's do it. The final momentum, now here's where the subscripts get a little goofy. A mechanical pencil comes in handy because you can write kind of tiny things. So the final momentum is the mass of, now I've got A plus B. Right? You have to add those two together. Right? Where M, A plus B is the mass of A plus mass of B. If you want, there's no reason why these are decimals, right? There's no reason why you couldn't just go and maybe this is better to do it in brackets. Right? If you want to just do it that way, you can. I like the M, A plus B, but that's me. If you want to show the two M's added together, that's fine. The key idea is you got to add those masses together. I had, instead of, like, M A plus B is equivalent to bracket MA plus MB. Like I just kind of simplified that a little bit, right? So it's a new mass of A plus B. Okay? If you want to, I like it this. If you prefer to write it out as MA plus MB, go right ahead. I understand that. Okay. And of course that is 300 grams or 0.3, right? By the way, this is why I yell at you in grade 11 for showing your work. Because I know what's coming here. Okay, so why is the final momentum that it's minus 0.2, right? Because the initial was that, and that is equal to 300 times the velocity of A plus B. And so the velocity of A plus B is minus 0.67. I'm waiting. Does it make sense? No? John?
Where did that 3 come from?
The mass of the, remember our carts were,
Okay.
let's go back here, right? We've got 100 grams and 200, right? So the total mass when they schmuck together is 300 grams or 0.3, right? And so the final momentum is minus 200 because that's what the initial was, minus 0.2,
And then that's the final.
right? That's 0.3, yeah. That decimal place is really quite annoying, isn't it?
Slightly.
This was grade 3. Mrs. Murray would be smacking my hand with a ruler.
Such more.
She was my grade 3 teacher.
How do you?
Trust me, when you get your hand smacked by a ruler by Mrs. Murray, you remember.
My grade 3
I
teacher?
remember all my teachers.
Don't even repeat about it.
I remember watching kids get their certificate.
So the final, how the heck did we get on that story?
Because you didn't go to
Oh yeah, right, 'cause I made those mistakes. Okay, how about you try one? Now, I get the stumbling block is how to organize it, right? I get that, okay? We'll get there. So just give this a try, okay? If the mass of cart A is, we'll just say 4 kilograms, get rid of these stupid decimals. And B is 2 kilograms. And the velocity of A is 6, and the velocity of B is 0. Oh, it's at rest. So it's this kind of thing. So we got 4 and 2, right? So what happens? That one's at rest. What happens here? What happens to the speed?
Friction's going.
Why does it go slower?
Friction. Because it has
Or we,
more weight.
Because it has more mass, right? Right?
What do you mean slower?
Well, watch how fast this cart's going, okay? And then compare that to the mass, to how fast it's going in, right? So I mean, just assign some number, right? This one is more massive too, right? So it's going that fast. Why does it slow down? Because it's now, in fact, 1/3 more, right? Like if this is 500, 500, 500, the moving part was 1,000. Now the moving part is 1,500. So it's going to move slower. Okay, so find the velocity of the combined mass after. It looks like this. Oh. I know, I knew the answer was there. So, what is the momentum before? It's going to be, now we do have A and B, right? So, it's going to be MAVA plus MBVB. I would suggest you do this on, have you got room to do this on the side? Okay, so mass of A is going to be 4. The velocity of A is 6. Mass of B is 2, but its velocity is 0. So the initial momentum is 24 kilogram meters per second. You should all be able to do that. 24 kilogram meters per second. And that is also equal to the final momentum. We've proven that. Momentum must be conserved. So what makes up the final momentum? Well, that's going to be mass, but now it's combined together, so it's mass of A plus B together, well, right? Times the velocity of A plus B. And how much is the final momentum? 24. What's the mass of A plus B? Now, I guess really, you should write that somewhere, I guess. Oh, it's 4 plus 2, right? I mean, it's so simple here that, I mean, everybody knows it's 6, right? So that's going to be 6 times the velocity of A plus B. And this is 6 times, so what do we do? And so the velocity of the combined system is equal to 4 meters per second. What do you think, Bud? Doable? Yeah.
This is like, is this an easy one or this is an easy one?
It's not the hardest.
you see one of these on the test.
Yeah, this is fairly straightforward. Okay? I understand. I honestly do. I get you don't quite know how to set it up, right? You don't know how to explain. You could probably, if you just had a calculator, you could probably figure out the answer, right? I get it. That's why doing that practice is important. And looking at the solutions that I give you. All right. Elastic collisions are a little different. Inelastic means put together. What do you think elastic means? Balance, right? What if one is more massive than the other? What happened? Watch the speeds. I'm going to try to make the speeds the same. They work. Right. But this one clearly does what? goes faster. How come? Because the overall momentum at the start, because this one's more massive and maybe going faster, right? The overall momentum is this way, so the overall momentum after has to be this way, which is why, to make up for it, this one has to go faster, right? How do I make this one go that way? Faster. Really rifle on, right? Okay. If I make this one go slow, does that go faster? How much faster? Why twice? Twice as much mass. You guys get this. I think you intuitively get this. It's the writing down that's the hard part. Okay? Elastic collisions occur when objects rebound off each other without a loss of kinetic energy. Okay? And here's a little video that shows it there. Momentum transfer, a little joke. You can look at the numbers if you want and figure it out. But I mean, the big truck has a lot of momentum, and so all of that momentum is transferred to the little car, and it goes fast like that, right? When the little car runs into the big truck, he doesn't go very fast, right? Now, perfect elastic collisions occur between atomic and subatomic particles only. In the lab, they use pool table or stainless steel balls. Like this thing here, when it works, only goes so long, and eventually it runs out of energy. Why? Because that kinetic energy is converted to heat, and the steel balls actually do. You can't feel it; they're warm. But if you had a really accurate thermometer, you could tell. Okay, so I think I've got one last one, right? Yes. Suppose, we're almost at it. Suppose the two carts involved are now elastic. So we've got 100 grams, 200 grams. Now actually, just stop for a second. Let's go back here. Just a point of order, I guess you could say. 100 grams to 200 grams. I had to worry about all these decimals, but then at the very end, did I change anything here? Does it work if you leave it in grams? Yes, it's just your unit for momentum is not kilograms, right? So, but I still have to change it, which I will do. All right. Now, what do you guys have? Do you guys have the picture? Oh, perfect. Okay, so find the speed of part B after the collision. What's different about the setup? There's only one small difference. What's different? B is at rest, that's true. I hadn't thought about that one. There's two. No, it wasn't one at rest before? Yeah, one was at rest here.
This one doesn't say it's at rest though. Yeah, ours says it's moving. Yeah. Well, it's not there.
B is at rest right there. The difference is the carts don't stick together. So there's none of that M, A plus B. Now it's MA, MB. And I'm going to introduce one more piece of notation that you're really going to hate. Well, some of you might like it, I don't know. Here's where I like the PI is PF. I don't know why I like it this way. Maybe I was shown this way back in the day. What is the initial momentum made up of? MAVA plus MBVB. And on the right-hand side, MAVA plus MBVB, because the masses are separated. Now, I just wrote the same thing on both sides of the equal sign. Is the velocity here A, and this VA is equal to, is it going to be the same as this VA? It's not, right? They're not going to be the same. So they can't be left as the same variable. We need some way to distinguish one as prior to collision and one to after collision. Okay, so there are a multitude of ways. One, you could say 1 and 2. Like, okay, you could do that. Don't write it down. You could say I and F, and so you get another subscript, VAF, VAI. Professors love that kind of stuff. Here's what I like to do. You put a little apostrophe there and you call it prime. And all it does is it indicates after collision. I like it because it removes the subscript and it it's a little bit more visual. It's not down there, like you can see, it's just more visually different than this. So you would read this as MAVA plus MBVB is equal to MAVA prime plus MBVB prime, where prime means after collision. How do you like that? That's okay? If you want to go 1 and 2, you go ahead. If you want to go I and F, you go ahead. If you want to go before, write out before and write out after, go ahead. I'm using prime. Okay. And actually, once you get that far, the math is relatively simple. So what's the mass of A? 0.1. The velocity of A is 2. The mass of B is 0.2. The velocity B is, oh, it's 0. Is that nice? Is that handy? Yeah, it makes things a little simpler. The mass of A remains 0.1. VA prime is 2. It told us this here. Oh. You know why I'm angry? What's the problem? I can only find one velocity after, right? I need this number. Okay, so if I say the velocity of A, I guess it's VA prime, right? VA prime is at rest. So this 0.1 times 2 is 0.2. That goes away because it's 0. 0.1 times 0 is 0, goes away as well. So 0.2 VB prime, and then suddenly you've got 0.2 is equal to 0.2 VB prime. Divide both sides by 0.2, and your VB prime is equal to 1 meter per second. Yes, that's what I just did, right? Yeah.
Just like this guy doesn't have a velocity, the rest I just have.
I guess, yeah, I guess,
You just assume.
I guess that would, maybe that's what the question was designed, yeah. Is that it, because they don't give you the value of A after, it must be 0. Long day for you, eh? Yeah, I appreciate your concentration. Do you find, did it make more sense when you're, a little more focused? And did it help that I warned you ahead of time? Yeah? Did you?
I just laughed at it.
Did you?
What was the message?
Can I read it out? Can I read it?
It's like FYI.
What I feel like I should do is do these example questions, but I'd be foolish to push my luck.
Yeah, do it.
Okay? So, if you're inclined, if you think it's good for you, I would suggest you've got 3. Do you have these?
No.
You don't. Okay, I'm going to hand these out. There's 3 sort of sample ones. It would probably be a good idea to have a look at them and try them. I'm going to do them first thing tomorrow, and then give you time to work.